Hello. Hello. Test. Hey guys. Thank you guys for coming today. How many of you guys came from the U of M Summit Security Conference? Yeah, there we go. Sorry for any confusion in terms of location. We were originally going to have a reception at Sava's, and then we decided to relocate it here, so all the great food upstairs is compliments of them. Feedback. It's all right. So we have a great speaker today. Before introducing Joe, I just wanted to open up for any contributions from the audience, events that are coming up, job postings, other announcements about security or tech. We'll throw the box at you, Joe. You want to whip it at him?
By the way, this box is a microphone, so if you have a question, you have to speak into this.
So which this end of it is the microphone. That's really cool.
Got it.
So I don't know how much of this stuff is going to come up during Joe's talk, but tomorrow evening up at the Hackerspace i3 Detroit is an electronics lab orientation, and we have a lot of tools for doing hardware hacking reverse engineering that kicks off at 7 p.m., I believe. So you're all welcome.
Where in Detroit is it?
You had to go there.
Just drive to Detroit and ask around.
No, it's so the space is called i3 Detroit, but it's technically in Ferndale, which the other space in Detroit loves to give us guff about. But yeah, just i3detroit.org has the address, and 7 o'clock for the orientation. And we have all the stuff. It's not that messy, though. Cool.
Just toss it.
Just toss it. Okay.
Whoa. There's a talk. Does it work?
Yeah.
Can you hear me? There's a talk at Eastern tomorrow with their information assurance group. The speaker's name is Thomas Banya.
Tomas Banya.
Okay, yeah, go ahead, Jessica. Take it away. Okay, so he is the global security lead for HP. It's free, open to the public at Eastern's campus, Roosevelt Hall, room 6.
So it's down in the basement. Definitely park there. There's parking across from Tower Inn that's free. Or you can park at the Peas lot, which is metered.
You
So,
want
yeah.
the
5:30, yep. Sorry. I'm done, sorry.
Jessica?
Oh, I'm good. That was all. So I just added to it.
Anybody else? Cam, one of our software engineers, I don't know if he's in the audience, but he said there's a hackathon going on somewhere in Ann Arbor after this event. So if you haven't been to enough events tonight, you can go somewhere in Ann Arbor to the hackathon. Does anyone know where it is? Vikas, do you know? It's called Fuck It, Ship It. It's the hackathon. The Shift House. Okay, Oxford Housing. We have a lot of vague directions here. Just wander around Ann Arbor and Detroit and Ferndale, and people will want to hang out with you. On Monday, given that this is Cybersecurity Awareness Month, there's like 10,000 events. And there's the North American International Car Show, Cyber Summit at Kobo, and that is hosted by the state of Michigan. And a lot of good speakers and sort of different tracks of cybersecurity there. I think it's all day Monday and maybe part of Tuesday, if anyone knows more. There's a website. Sunday and Monday? What's the 25th? Is that Sunday? Yes, Sunday and Monday. So that's in Kobo Center in Detroit. Go to just search for Michigan Cyber Summit, and it'll come up if you want more details. Anything else that we're missing? Jobs.
All right, Duo has jobs. Have you guys heard about Duo's jobs? So we are currently recruiting. We have some high priority jobs that we're looking for right now. So we're looking for another 1 or 2 DevOps engineers or even a back-end engineer to be on the DevOps team. What's that one that's disrupting it? No, no, guys, it's not. It's not. I want the catch box. All right, we're gonna try this one more time. We're also looking for another Windows engineer to join the team. So if you're looking to be an expert at Duo and something, we could certainly use your support. In that category, we have a small Windows team that's gaining momentum there and a lot of projects to do. So if that's your area of expertise, let us know. Also, if you see any listings on the Duo page and you have a referral, we will start to be offering an external referral bonus in Q4. So eventually there will be a link to the jobs page and all of those things once we get that going with our marketing team for our website. But in the meantime, if you guys have somebody to refer, if you let me know, I will definitely get you a bonus over for it. So all taxable, of course. But thanks, guys.
Cool. Anything else I'm missing? For folks that are new here, this is Duo Tech Talks. I'm John Oberheide from Duo Security. We'd like to have a lot of, oh my gosh, this is throwing me off. We'd like to have a lot of external speakers here, really smart folks from the security space. And Joe is certainly one of those. All of our videos are online, so if it's your first time here, you can look back at all the other great speakers that we've had and watch the videos on our YouTube channel. Feel free to check that out. I had no better way to introduce Joe than to sadly just read his bio. So we'll do that. Joe Grand, at Joe Grand, his Twitter handle, also known as Kingpin, his handle, is a computer engineer, hardware hacker, product designer, teacher, advisor, runner, daddy, honorary doctor, TV host, member of L0pht Heavy Industries, and a proprietor of Grand Idea Studio, grandideastudio.com. Joe is an amazing luminary in the security space, has a long history of awesome work, is infamous for building the DEF CON badges, the cool kind of hardware-oriented badges that were displayed and handed out at DEF CON over the years. But is also just an all-around great dude and has a lot of funny stories if you take him out for a beer, which we hope to afterwards. But give Joe a warm welcome.
Awesome, awesome. That was a great introduction. I couldn't have written it better myself. We actually know each other. It's not like this is the first time we've met and he's just like reading the bio, but that was well done. Thank you. All right, yeah, my name is Joe Grand. Thank you guys for coming and choosing to spend, I don't know, an hour or something with me. And for those of you on the internet who are watching streaming or maybe watching later, thank you for watching from the safety of your home. Yeah, we are going to talk about hardware hacking today. How many of you guys have done any sort of hardware tinkering, electronics tinkering? Everybody. Okay, so why am I giving this talk? Okay, John O hasn't given hasn't done any hardware hacking, so this talk is for him. And this is not my office, by the way, but this is what your office will hopefully look like at some point. So this talk basically is a tools talk, and I wrote it kind of with the security community in mind, but thinking about, all right, if I was getting into hardware and hardware hacking, where would I go? What tools would I want to look for? Sort of thinking about like if I wanted to get into software or network hacking or something, like what would I do? Because there's so many tools, there's so many resources. It's like there's a conference every week, right? And it's impossible to keep up with actually what's going on. So this is basically like a list of the tools that I use a lot and that are accessible to people and that you'll be able to get and start tinkering with. And then, as you delve deeper into hardware hacking, you can sort of choose, some other tools and go and get more specific tools as you need to. So it really is just a tools talk. We'll have questions at the end, and then we'll throw that microphone at you and try not to hurt you with it. But that way, at least we'll go through the presentation, then, if you have questions, we can do that at the end. So yeah, the key with some of this stuff, as you'll see, it's general kind of tools. I do talk about some more advanced tools, but really the key to getting into hardware hacking is just knowing what tools are available. And as you approach a problem, it's like, oh, I see a debug interface on this board. What do I do with it? And you look through this list, and it's like, all right, I want to monitor the communication, just like you would do on a network, say with Wireshark or something. Now I need to decode the data. I have to figure out what's going on. But then there might be situations where it's like, I want to hack a chip. I want to hack the silicon die inside of the plastic package of this phone. That's a much harder thing, and most people don't have the tools to do that. And I'll show you at the end of the presentation some tools to do that. But most people don't have those tools unless you're Chris Tarnowski or somebody crazy that has the stuff in their house. But if you know what's available, you can outsource to those types of people, right? So it's like you don't have to know everything. You don't have to be proficient with every tool, but it's knowing what tools are available so you can actually get your job done or get your hack done, whatever it is. Oh, Jono has a question already. All right, throw the ball to him.
This is totally random, but what did Chris Tarnowski do, and how did he get those amazing tools to like decap and electron microscope all of those awesome chipsets?
Okay, so John just jumped to the end of the presentation. It's okay. So Chris Tarnowski is one of a handful of chip hackers. I would say he's one of the best chip hackers in the world. And as you see, when we go through our presentation, we're talking more about board level, circuit level types of work. Probing a board, listening to communication, monitoring signals, injecting our own signals, spoofing things. But Chris is doing what we're doing at a board level, but he's at a chip level. And he has an interesting history, which you should look online. But he got into it the same way that a lot of us did. It's just with different tools. I got into computers because my brother had a computer. He got into the chip hacking because his father was involved in that sort of thing-ish. So it's just, that just happened. And I think for a lot of us, it's just a natural thing to do. Like, this is what I do. It's not my job, it's my life, right? Like, I design electronics, I hack electronics, that's what I do. And the same thing with Chris, and the same thing with a lot of people in this community. It's just not, it's not just a job, it's a way of life, it's a passion. But he can handle things a lot of times if we're working on a project and it's like, oh, there's a security fuse set on this chip and I can't extract the firmware that I want to use to start reverse engineering the code to figure out what that embedded system is doing. Send the chip to Chris and he'll fix it on the physical die, and then you can read the code out and do it. So it really is like a multi-level process. But yeah, he's one of a handful of guys, but this hardware community, the hardware hacking community, is really growing, and there's more and more people getting involved, and a lot of it is because of the accessibility of the tools and just the openness of people willing to help other people. So the hardware hacking process is kind of there's lots of different steps, but for the tools, I've kind of broken it down into the three. So monitoring signals, analyzing what's going on between chips, perhaps, or maybe through an external interface to the outside world. And then maybe you want to manipulate that data, inject new data to it, almost man-in-the-middle types of stuff, replay. A lot of things, as you see, if you sort of look at history of hardware hacking, hardware security is horrible. No offense to anybody that's actually designing, secure products. In general, hardware security is really bad. And a lot of these tools, a lot of the classes of attack that I've been talking about for way longer than I want to admit, are still accessible. So it's like, you think about replay attacks or man-in-the-middle in a software perspective or network perspective. People know about those. Designers try to prevent those types of obvious attacks. On the hardware side, not so much. So that's the thing we want to do, inject and manipulate data, which usually ends up working out pretty well. And then we'll talk about some imaging, kind of non-destructive imaging, and some destructive sort of things. More advanced. This is kind of chip-level stuff. But yeah, just trying to dump a whole bunch of tools on you. So let's see, what do we have? First one, oh yeah, the oscilloscope. Okay. This is probably my favorite tool in the world. I'm in love with my oscilloscope. I actually have a video somewhere online, and I was like hugging my oscilloscope. You'd have to see it. And I showed that to my son when he was little, and he goes, "Daddy, why are you hugging the oscilloscope?" And I'm like, it's a long story. I'll explain it when you're older. But a scope basically lets you visually see an electrical signal and how it changes over time. And I know that sounds really sexy, but what it means is you can start probing around on a circuit board and say, oh, what is this signal doing? What is this signal doing? And being able to visually see it. And that's really important, right? Just like if you're on a network and you're looking at data, it's like if you can't see what's going across the network, you can't start your attack. Same thing with hardware. The oscilloscope is sort of what I use for the first level of probing on a board to see what signals are doing what. Maybe I don't know what they are, maybe I do. based on other information that I've reverse engineered. But it's a way to gather clues and gather information and capture data. So it's a very, very important tool. And it shows you actual analog waveforms. So it's not just ones and zeros, it's a level below that. It's, you know, if it can be any variation of waveform. So it's a very powerful tool. Lots of different ones out there depending on what you're into. I sort of provide, for all these slides, I provide like professional tools, some hobbyist tools, and then open source ones as well. So there's lots of options of things here. And then I have some examples for some of the tools I threw in. This one, using the oscilloscope, was one part of a project that I'd worked on a long time ago, hacking the San Francisco smart parking meters. And this was right when I'd moved to San Francisco. I don't live there anymore, but when I did, I was like, this is awesome. The parking meters in San Francisco use smart cards. I had never used smart cards before, and you know, they were very well established in Europe, but not really in the United States that much. And we're finally starting to see them on our credit cards and sometimes for other pay types of systems. But this was, you know, parking meters were using smart cards. I said, I want to figure out how this system works. I'm going to use an oscilloscope and monitor the communication between the smart card and the parking meter. And let's see if we can capture data and figure out what it actually is. That was the main part. There's a whole presentation about it that goes on for hours and hours. But the short story is that I was able to monitor the communication. I had this, you can't really see it in the slides, but I had this shim that would, with a socket on one side that I plugged the smart card into, and had a bunch of breakout lines for each of the different contacts on the smart card. And on the other side of the shim was the actual smart card pads that would plug into the meter. So I was working on a live parking meter on the street, monitoring all this communication. And it was San Francisco, not a big deal. Maybe nowadays people would be like, what are you working on? And you just say, it's a clock, or you know, whatever. It's an art project, or whatever it is. So what I ended up doing is using the scope, capturing lots and lots of data. This was a stored value card. So you basically put the card in the meter. It will show you your current remaining value, and then it will start deducting money from your card and adding time to the meter. And then you take the card out when you're done. So it was I thought it would be a very simple system. And I ended up just taking lots and lots of captures of different types of cards, different value cards. I'd leave it in for longer times, take it out, and I just ended up with a bunch of waveforms that ended up, it looked like high and low. So it's some sort of data stream. And once I had enough of that data, I tried to figure out, all right, how can I figure out what it is? You know, I don't want to just look at waveforms. My oscilloscope has a feature called digital decoding functionality, and that's something that's more common in logic analyzers, which I'll talk about next. But if I know what the type of protocol this data stream is, then I can actually see the bytes of data. And you can see down here there's 4 bytes of data. This was an asynchronous serial communication interface, and I'll talk about that later as well with another tool that could be useful for us. But I was able to eventually get the right setup for this asynchronous serial communication, and I could decode the bytes. So these are actually the bytes of data that refer to that data stream that match what's called the answer to reset, the ATR value of a smart card, of this type of smart card for this meter, which was Gem Plus. And I think 2 of the bytes is like the manufacturer code for Gem Plus, the smart card manufacturer. So I knew I had the data right, and eventually I could do a replay. I built an emulator to replay all of this, all the data, and then I figured out how the value was actually stored on the card, so I modified my code to have what I thought would be, you know, possibly unlimited value. And that was all done with a microchip pick and write some code. And then I actually found a smart card that some cable TV hackers had been using that had a general purpose microchip pick, unprogrammed microcontroller on the smart card, so I could put my emulator code into the smart card and plug that into the meter instead. So here, I'll show you a video of it. Of course, you know, all this stuff is available online if you really want the details. And the code for an emulator is online too. So here's the result. I'm standing on the street, holding the camera, and then holding like my then, I don't know, 1-year-old baby who's now 7, and possibly watching this, trying to figure out what I actually do for a living. So there's my emulator, put it in. So in case you can't see that, $999.99, which means I could park in San Francisco for, I don't know, a few days without having to refill it. But so this was, you know, using the oscilloscope was the main part. Of course, this also goes into figuring out the interface, spoofing that information and stuff like that. But with the oscilloscope, I could actually see where the data was coming, when the data was going from the card to the meter, and when the data was coming from the meter to the card, because there were slight voltage differences between the two. Even though it looked like one big data stream, there were slight differences. And that's the only way I would have been able to tell who was talking when. As opposed to with the logic analyzer that we'll talk about next, you're only seeing ones and zeros if they go above certain thresholds. It's not as good. So the oscilloscope is key. Oh, we have a question.
Do you have any challenges with speed of communication? You know, a parking meter probably doesn't send that much data, but if you're trying to do an oscilloscope on a 3 gigahertz CPU, that's a lot of data that's going through it in a small amount of time.
So the question was, are there any sort of speed issues with capturing data of systems that might have more, faster data? Most of the time with serial interfaces, especially with smart cards, the transfer speed is fairly slow, and most oscilloscopes are well capable of capturing. There are some hobbyist oscilloscopes that are cheaper, or lower cost, I should say, that might capture more slowly. But if you encounter a higher speed system, you could always rent a high-end oscilloscope, something that's $50,000 normally. You rent it for a week for $1,000 and do your attack. But for most types of external interfaces, serial interfaces that you would connect to that you would typically be monitoring, you're not going to run into super high-speed stuff. That's going to be when you're on a board level looking, say, between a microcontroller and external memory or a crypto processor, or Northbridge and Southbridge on a PC or something like that. Do we have that ball, by the way, or that cube? Can you throw it to me? Don't hit me. You can do it underhand. Okay, good enough. Thanks. Now I'll throw it at the next person. So yeah, that was the oscilloscope. Most people get started, though, using a logic analyzer because they are a little more accessible. And a logic analyzer, you're basically just looking at ones and zeros. So you're not looking at the actual electrical voltage levels. With the analyzer, if you're above a certain voltage level, you're a 1. If you're below a certain voltage level, you're a 0. But it will give you lots of ones and zeros. And the cool thing about logic analyzers is all of them actually have digital decoding functionality. So you can start, you could take a guess, either educated guess or through data sheets or whatever other reverse engineering, figure out what the protocol is, and then see the actual data bytes, just like I showed you with the oscilloscope. All sorts of different brands. Probably one of the most popular is the Saley Logic. That's a really good device, very accessible. The guys that create that product are two brothers. One is the hardware guy, one is the software guy, based in San Francisco. And I love their tool because they will take feature requests from the community and people can upvote them and stuff. And they're continually maintaining their tool. And it's one of these tools, as you'll see throughout the presentation, there's tools that are created either by the community or by hackers. And those are the ones that I feel like are very important. So those guys really listen to the community and try to make things accessible. Though the larger companies are great too, but you have different sort of support. And a lot of these tools also I didn't mention we're basically just taking advantage of legitimate tools that normal engineers would use to design products. We're just using them in a way that they weren't necessarily thinking about. We're just using the tools that are available. So that's kind of cool. Here's a screenshot of, this is just a simulation of the Saley. And so if you're looking at, say, here's the SPI interface or an I2C interface, an inter-chip communication interface between two chips on a board. If there's a microcontroller talking to some external device, maybe that has a crypto key stored in it. A lot of times, that data will be transmitted in the clear. And it's like, I want to figure out what I'm looking at. So here we see like the SPI decoding is set up, and there's I2C. Here's CAN bus. So if you're hacking on cars, and CAN is a very common interface on cars, it's like, I want to hack the CAN bus. Let's see what data is coming across. There's all sorts of different stuff you can do with these different protocols once you figure out what the protocol is. And maybe you take a guess at what it is. But having the analyzer is a huge tool. And this is usually the next step, right? It's like once you identify what the interface is, possibly using the oscilloscope, then you really go to town with the analyzer. Here's an example from my friend Bunny. This is a really old example, but still totally relevant today. And it basically shows that sometimes you can't use an off-the-shelf tool. So in the case of a logic analyzer, usually you can get by with one. But this was part of his work with the Xbox back in the day, where he wanted to monitor communication between between the North Bridge and South Bridge on something called the Hypertransport bus, which is this high-speed 200 megahertz bus, which was really fast back then, but it's still pretty fast for engineers to deal with today. He wanted to monitor that bus. He didn't have the equipment to actually do it, so he created his own tool. And that's something in the hacker community we see all the time, at least on the software side, of like, oh, there's no tool to do whatever, I'm gonna just throw it together and make it. Same thing happens on the hardware side. So he basically created his own shim that would sit down on the bus that he was interested in listening in on, scraped away the solder mask, like the protective coating on the circuit board, tapped his board down, converted those signals into ones and zeros, and then decoded everything. And through this work, I'm oversimplifying it, of course, but through his work, he was able to put out a secret key that was used for code signing, and then he could execute, his own games on the system and everything, which ended up, I think his research ended up kind of fueling the mod chip industry as a byproduct. But it's, super cool, and sometimes you have to think about that. It's like you encounter a problem and you have to create your own solution and, preferably share that with everybody else. So taking it one level higher than that, logic analyzer looks at ones and zeros. Protocol analyzer looks at the actual higher level protocols on top. This is really, really useful for systems like USB or HDMI or Ethernet. Things that if we were just looking at ones and zeros, we would kill ourselves. Like, it's just too much data, too much going on, way too high speed. We can't analyze what's going on. So protocol analyzer, typically what you would do is use it as kind of a man-in-the-middle type of device. So you would have, say, your target device plugged into a protocol analyzer, and then that's plugged into your host. And you're capturing all of the data going back and forth. Sort of like what I did with the shim, just a little more advanced. And this is something, if we encounter a system that has some higher level protocol, this is the way to do it. We would capture all the information to see what data is coming across. Maybe we change inputs to see what things happen on the output and go through the process. Lots of different products available, some open ones as well. Michael Osman has been working on Project Daisho for a while. He announced it a few years ago, and it sort of got pushed to the side because of the HackRF work that he's doing, which I'll mention. But trying to make an kind of open source tool to let people work with high-speed signals that they wouldn't necessarily have the equipment to do unless they went and rented it. But yeah, lots of stuff going on in that space. It's really, really cool. And again, it's like being able to visualize what's going on. Just like you're using Wireshark, that's the way to figure out what data is being transmitted. And then you can say, okay, I want to try to spoof that information, or maybe it is transmitting a key in the clear that I can reuse, or whatever it is. You don't know until you start visualizing the data. This one here is a screenshot of a USB protocol analyzer, and anyone that's ever worked with USB, probably recognizes this, but doesn't want to because it's such a pain to work with. But this is, all of the data that's coming across. It's going to show you, click on things, and you can view, here's a configuration descriptor of what the device is sending to the host. All sorts of crazy stuff you can do, and just very useful. So protocol analyzers are good. Here's the HackRF. So those tools are mostly used for physical monitoring of signals on boards. But now we're seeing a lot of devices that are wireless, right? Internet of Things, everything's connected, and it's either physical connection to the internet, or it's through Bluetooth or Wi-Fi or whatever it is. So there's a whole community now of people using software-defined radio to start working on these types of systems. I will mention that this, we're still talking about kind of signal monitoring and stuff, but there is some heavy overlap sometimes with the tool. Is like stuff with software-defined radio where you're basically doing all of the RF radio front end and hardware, but then all the intelligence, basically creating your own radio and software, which lets you receive things. But a lot of these tools, you can also send data back. So you can start injecting data. So there is some overlap. But lots of research being done with software-defined radio. HackRF is really the main one that Michael Osman has been promoting. Tons of resources out there. So if you encounter a wireless system, typically you would go and, if you can, start with software-defined radio, try to figure out what frequency a system is transmitting on, what modulation scheme they're using, and then work to basically create your own custom radio system to decode that traffic. And again, it's all, like, hardware hacking is really all about gathering clues and getting pieces of information that you can then use. Here's an example. This was a guy that had been hacking his home alarm system. So what better way than to hack your own stuff so you don't get in trouble, hopefully? Though nowadays I'm not too sure. So yeah, he had this wireless alarm system, and he was curious, what data was being transmitted back and forth. Could he inject data? Could he, do whatever, defeat the system? So they had all these different wireless modules, and I'm simplifying this as well. But first he had to figure out what modulation scheme was being used, so he used some open source software tools along with the HackRF to figure that out, visualize the signal. I think I have a picture on the next slide I'll show you. He could visualize the signal that almost like an oscilloscope where you could visually see things, but he did what was called a spectrum analysis where you can see the signal strength and frequency of signals, which is really cool. And then with that, you can then figure out what modulation scheme is being used. So he did that, captured the signal, and then essentially created his own radio step by step to decode it, to get it back to ones and zeros, that then he could decode the data. And if you can control the input, like if you have a switch that says is on or off, if it's a door alarm or something, he can close the switch and see what data is transmitted. He can open the switch and see what data is transmitted. So you do that to figure out what's going on. It turns out in his case that the data was actually encrypted. So then he had to go through a whole other process of using other tools that I'll talk about in other slides to find the crypto key inside of, I think it was inside of memory somewhere, that he could now decrypt the packets and encrypt his own packets. But very, very cool. And here's it looks crazy, but this is the type of stuff that people are doing with wireless systems of, visualizing the data stream, guessing what type of modulation scheme it is. There's resources where you could compare something like this. Doesn't look like much. This is called a waterfall image. You take that, compare it to a website that has lots of different modulation schemes and transmission protocols and stuff, and help you narrow down what the signal is. So totally crazy. And all this stuff is open source. So it's like what people are doing in the open source community is just phenomenal. And here's a view of GNU Radio, the main radio tool people are using in conjunction with HackRF or with software-defined radio. To basically, create their own demodulation and clock recovery and convert it back to ones and zeros and decode that. So it's like, I'm not going to say drag and drop, but drag and drop to create their own radio. You just have to know what you're dragging and dropping to do it. So that's wireless stuff. Wireless is not this magical thing, right? We know that. There's lots of other wireless tools as well, so it really makes it easy. I think a lot of companies have this false sense of security of like, well, we're using Wi-Fi, we're using Zigbee. Our modules are communicating with Zigbee mesh networking. Like they're totally secure. They have encryption, but they don't realize like the crypto keys are leaked already. I think it's the trust center key or something. So then if you know that one, which is online, then you can monitor the pairing communication, and now you can start injecting your own data. So it's like, even though there's security in these systems, doesn't mean it's done right and doesn't mean it's secure. So lots of tools to start working with those systems. Ubertooth 1 these two, Ubertooth 1 and Yardstick 1 are Michael Osmond's as well. He's just amazing RF guy, amazing guy in general. So hacking Bluetooth stuff, general purpose RF, Wi-Fi Pineapple if you're doing any Wi-Fi devices. Let's see, femtocells. So if you're doing some sort of device that connects up to a cell network, use that to intercept data. Force a device to connect to you so you can figure out what's going on and then pass that data back to the network. There's some Zigbee stuff, RFiddler for RFID. So no wireless is safe. Let's just put it that way. Another cool tool is called the Chip Whisperer. And this is another tool that is not only monitoring, but also will let you do injecting. This is made by another friend, Colin O'Flynn, where he basically took a bunch of concepts and a bunch of techniques that had traditionally been reserved for the academic community and for some labs that had very expensive equipment, and made a platform that everybody can use, that the masses can use, if you follow along with the documentation. It's still very I feel like it's a complex task that he's making it easier. So Chip Whisperer really focuses on what's called differential power analysis or side channel types of attacks, where you're taking advantage of the fact that systems are leaking data in some way, whether they know it or not. Usually they don't know it. And that could come down to like the power consumption that a system is doing during an encryption operation. Depending on which byte of a key is being worked on, the power is going to be different. So with a tool like this, you can basically take hundreds of thousands of samples of different encryption operations happening and take a guess at like what key is being used or what bit of what what byte is, is it a high or low for this particular key, and narrow down and eventually break and extract the crypto key from things. Whether it's a smart card operation, whether it's some device that's doing its encryption, there's usually some minute changes in power. So it's very, very cool. Lots of academic work here, but then also he has like practical videos. The tool can also do things like glitching, which is more of a manipulating of a system, where you're causing a system to function very quickly outside of like a predefined range, which is something that's a topic of a whole other presentation. But if a system is designed, say, to run at 3.3 volts, it's like, all right, what if I drop the voltage really quickly as it's doing a hash compare or a code signing check at boot up or something? Like, can I skip over that operation? And a lot of times you can. So crazy things here. Very cool tool. He got second place in the Hackaday Prize competition last year, and first had this system, which is a more professional system, and then he came out with an even more accessible hobbyist system that was on Kickstarter that you can get now. So it's a smaller system to really start working with those types of attacks. So that's sort of monitoring, getting an idea of the data that's coming across, of what a system's doing. Then we go into manipulation and injecting, and possibly working with the system to change it in some way or have it behave in some way. Soldering iron, of course. If you're going to start tinkering with electronics, this is one way to do it. I even put an open source option for soldering irons. If you're that diehard about only using open source, you can make your own driver board to heat up like your own soldering element. Yeah, it's crazy. But I just ended up buying one because it's easier. So different types of soldering irons, different types of tips. It's really just one of those tools that is useful to have if you want to solder wires on, or if you want to probe things and maybe cut a trace and solder a wire on to see what's going on, or take a part off a board. This stuff here called Chip Quick is a neat little tool that helps you remove certain types of parts off of boards, called surface mount components. And those are components where the part is mounted to the top side of the board or the bottom side of the board, as opposed to through-hole parts where you have a part with legs that stick through the board. Traditionally, with surface mount parts, you have lots of pins coming off, and you can't unsolder each pin at a time. It's too hard. I'll show you another way to do it as well, but Chip Quick is just kind of a cool little trick to use if you have an individual part and you need to remove it from the board in order to, say, read the contents of, if it's a memory device, read the contents off of it, or reprogram the firmware in a device or something like that. I think I have a video of this, but it basically uses like this low melting. It's a bismuth-based solder. So it's a low melting point solder that mixes with the normal solder that's a higher melting point, keeps the whole device, all the solder molten for longer, and you can like push the part off the board. It's crazy. So this is a good way if you don't have access to what I'll talk about next, which is like a reflow or a hot air station. Getting involved. This is a $15 kit you can get on DigiKey and a bunch of other electronics distributors, and start experimenting with like, oh, I want to take the part off the board, because now it is something easy to do. So here's an example of using a circuit board that I use. I have a hardware hacking training class that's like a 2-day course of hands-on exercises and me blabbing about things. So I'm using one of those boards. There's this middle part here that's an SSOP 20 package, very fine pitch package. And I just squeezed on what was called flux, which is like a chemical component that helps with heat transfer. And now I'm putting on the alloy, basically like short-circuiting all the pins and stuff. Doesn't really matter. And you'll see, like, as soon as I get the alloy onto all the pins, I can, like, there we go, boop, just push the part off the board. And then I'll clean it up, and you'll see, I'll clean it up and get it ready, like if I wanted to put another part on, or if I wanted to tap things on there. I have some test points hidden under there as well that possibly, test points are signals on boards that engineers put there for testing or for programming. I just happen to hide them under there for some reason. I don't know. So yeah, just use the alcohol pad, clean up all the flux, make it look nice and pretty again. And now you're ready to either put a new part back on or start tapping on to those pins a little easier, or maybe you want to access the test points or whatever it is. And if you had the part, you would need to clean the part off using the same process. I had a desoldering braid that would clean up the solder from the part, and then you could put that in another system or whatever you're doing. But yeah, just sort of a kind of a fun one to show off. what other people use is called a rework station, and they come in varying types. Hot air is the most common. So if you want to remove a part, here's a picture of a guy removing a flash memory device from a board. It basically just blows really directed hot air at a device. So, if you find the right sales guy, you could like focus him on a part and take a part off the board or something. So, I don't know, just blow hot air on it. Sorry, salespeople. I don't get out much. So this is kind of a more, this is a common one as well. The risk, though, with hot air especially, but with rework stations, is you might not necessarily focus your heat just on that one part. So some people put what's called Kapton tape, maybe use aluminum foil around the part to dissipate the heat and just focus the heat on what you want. In the case like this, where you have pins, another really fine pitch part, but there's lots of other parts around it, chip quick would work, but you run the risk of like the chip quick stuff getting all over the board. So sometimes it's going to be good, sometimes it's not. Just like every other, you want to have lots of tools in your toolbox for specific purposes. So in this case, hot air would be the way to go. And you would basically have the hot air and like different types of nozzles that you'd put on for different packages. There's also way more expensive systems that will do infrared, so it would heat a system with infrared or with laser to really give you focused heat on a device. But this type of thing, this particular device is like $150,000. So if you happen to have some spare change, you could go with something like that. But that's really saved for like academic institutions, companies doing digital forensics, law enforcement that are extracting memory devices from mobile phones and dumping all the data off using a general purpose device programmer, which I also show you in the slides. This is a higher end device, but this lets you get all sorts of very specific heating profiles so you don't damage parts or run the risk of damaging parts. But yeah, I just wanted to show you like what the top end is. If you can find one of these, like say in the surplus market or something, like get it. Like that would be awesome. Or tell me about it. So then a reflow oven, you take a part off a board, maybe you reprogram it, you do something, put it back onto the board. You could possibly hand solder it, sort of the opposite of using the chip quick. You could do something called drag soldering, where you're basically putting a bunch of solder on all of the pins of the part and then cleaning it up with some desoldering braid to get rid of the solder joints. That's kind of a low-cost technique. But if you have a reflow oven of some sort, that way you can properly follow the solder reflow profile. You don't run the risk of damaging the part as much. And they are accessible nowadays to people outside of just normal contract manufacturers. So I figured I'd put it in. It's a good tool to have. You can either buy, like there's one from somewhere in China. It doesn't even have a company name. It just is called T962A. But that's like what everyone uses. Who knows where it comes from? I wouldn't plug it into your network if there was like a network connection on it. But who knows? It's like this generic device that works okay, but then people have like modified the firmware and hacked it to make it even better. So it is really a good option. Or you could take a toaster oven and hack your toaster oven to also follow the correct temperatures. And that's what I've done. This is my oven here. And yes, you could always just do reflow. And if you want to solder a part on a board, you have some solder paste, which is like paste with solder balls in it. Turn on your oven to full speed, full temperature broil, and it would solder. But usually you want to follow the recommended reflow profile, which is what these hacked kind of controllers do for toaster ovens. But yeah, a fun tool to have. Just don't cook in this after. Like, have a separate toaster for that. Yeah, don't make cookies. Because a lot of times the solder is lead-based, and you'll have all sorts of fumes and stuff in there. I actually went to an expo sort of engineering conference one time, and they had a giant reflow oven that was used during production manufacturing. But instead of circuit boards going through, they were actually baking cookies in it, which was awesome. Yeah. I don't think anyone got sick. Except 20 years from now, we're all going to have lead poisoning or something. All right, so say we take the part off the board. A device programmer is another tool, super, super useful, and something that a lot of people involved in hardware hacking, I feel like, don't even know exists. So it's very important, and it basically is a tool, a legitimate engineering tool, that lets you put a component, a memory device, into it, and it will read it and give you the contents of the memory, or let you change the contents and write it back. There's all sorts of different types. Some of the brands support up to hundreds of, tens of thousands of devices, different device types. Sometimes you can get lucky, and depending on the memory chip, you don't even have to remove it from the circuit board. You could either find test points on the board, or maybe there's a programming interface or something else on the board itself, solder wires to those, bring it directly to the device programmer, like this one in the middle. I was messing around with the authentication token a long time ago, which turned out to be really bad, so you should use Duo, types of stuff. Yes, you can do it in circuit, as long as the system isn't actively talking to the memory at that time. So there's little tricks you can do to disable the microcontroller or do whatever, so you don't have to take the part off the board. But they're very powerful tools. If you encounter something called eMMC, which is a type of memory that basically is NAND flash with a controller on board, so it sort of acts as like a SD card or something that has a file system. Really common for Linux-based systems, for mobile phones and stuff like that. You can either take the part off the board, put it in like a $30, $40 little programmer from China that's less general purpose, more specific purpose. Put it in a socket, stick it in your USB port. Use a separate laptop, of course, for that, and DD the contents right off. So yeah, lots of powerful tools, but device programmer, hugely important, and it will save you a lot of time. There are hacker-specific methods that people have done, but a lot of times it's like, all right, if you're going to go through all the effort of like hand wiring to these 100 different test points, like maybe you should just take the part off the board with hot air, put it in a device programmer, and be done. But again, it depends on the accessibility to tools. So there are hacker-specific ones that are out there, some really cool tools. A lot of it you're seeing coming from the game console hacking community, of people wanting to extract flash from the new game consoles, so the Xbox 360 or whatever the latest stuff is. Huge. If you want to learn about hardware attacks, check out the game console hacking community. They're doing amazing stuff. Them and the retro gaming community to preserve a lot of these games that might have security schemes in them. But really the point is, if you see a device with memory, whether it's a microcontroller or an external memory, anything, you want to get the contents off so you can start analyzing them and figuring out what it is. There's a whole suite of tools, binwalk, bulk extractor, IDA, of course, for doing firmware disassembly, radar. There are all sorts of tools out there. Once you get the contents off of the memory, then you can start going sort of a software approach to start disassembling things. Here's another tool, USB to serial adapter. This is going to be something that lets us actually start manipulating with the system and start communicating with systems a lot of times, where I talked about the parking meter had an asynchronous serial communication interface, which basically is a data interface that doesn't have an external clock associated with it. The timing of the signal is built into the signal itself. A lot of systems, especially Linux-based systems, are using UART interfaces or asynchronous serial interfaces to dump, to serve as an administration console or give you root access to the device. You would need physical access to the device, but that's okay a lot of times. If we can find those pinouts, we can connect either our logic analyzer to it, where we would see bytes and decoded stuff on the screen, or we can connect a USB to serial adapter like this thing down here, the FTDI friend, plug in our wires to that, plug that into our computer, and now we have a virtual COM port. We could load PuTTY, hyperterminal, whatever we want, and then see like the actual data come across. And if we find the transmit line or the receive line for the target, we can then start typing things on our computer and having the system react to those. So it's a very powerful interface, tons and tons of work, tons and tons of products that can be broken through finding the serial interface, whether it's just because you get root shell access right away, or maybe it boots you into a bootloader that is a partial access that you can like execute commands as root, or maybe you monitor, or maybe you modify the boot arguments, and then you reboot the system, and it will give you. There's all sorts of different ways. Basically, like this is one way. Finding a serial port and finding debug interfaces, both of those are like really good ways to access the system. Finding those sometimes is easy. Like I have there's different ways to find ports, test points, and other things, but a lot of times we'll see silkscreen markings, which are markings printed onto the board itself that engineers put there to make their job easier and to make manufacturers' jobs easier. So here we see VCC, which is power, ground, which is ground, our shared 0-volt reference, and then TXD and RXD, so transmit and data. Right there for us at the edge of the board. It's like, awesome. I'm gonna just connect that directly up to here, plug it into my system, and see what comes out. Like a lot of times it is really that easy. And these devices are like $10 or $15 each. Another question, hold on, I'm gonna throw this at you. For a guy in the front row, duck. Okay.
I was going to say I picked up a USB serial adapter to plug into my wireless router because there's some interesting things to put DDWRT and play around with that, but you needed to be able to see what was going on in the console.
Yeah, exactly. So it's something that it's useful for, for the developers to see what's going on.
And I'm not even a hacker.
Yeah, so it's a very common thing. Okay, you get throwback. So it is a very common thing, and you can get insight into what a system's doing. Sometimes you might connect to a UART output, and it's going to have a Linux login prompt. So you're like, oh, how am I going to get through that? There's other ways in through debug ports at that point, which I'll talk about. Maybe you modify memory, maybe you modify the process to let you in, or maybe you change some access control to give you log in as a normal user, get the password list, crack the password, and now through the UART interface, you can then log in as root. There's all sorts of different things. It's just like finding this stuff, and it's super, super common. Exploiters, exploit.rs, used to be the Google TV, GTV hackers. They have a lot of resources and examples of hacking embedded systems, ranging, from like normal network types of access points to like refrigerators to all the smart home appliances and stuff. Like, they do a really good job, so definitely check them out. So here's an example of that. This is a set-top box that a student had brought to a class of mine one time. He said, hey, I've heard that there was a UART interface. I've heard that this is running Linux. So I said, all right, there's probably some console access on there. Like, how do we find it? So we went through the process that we do in the class of looking for interesting connectors on the board. There's all sorts of different connectors and test points. This one down here is right near flash memory. So I'm like, all right, maybe that's a interface to extract flash, which would be a different type of attack. There's other connectors up here that go to like other boards that maybe aren't as exciting. But then there's these 2 4-pin connectors right near the microcontroller. And I'm like, all right, if that's, probably maybe those are 2 serial ports, just the fact that they're so close to that particular device and it's running Linux. So we took our oscilloscope, power cycled the board, because we know that with Linux, it dumps all that crap, on power up. So we power cycled the board, used our oscilloscope to look for interesting signals on the board. Once we noticed that there was one signal, when we turned on the board, we'd see all of this data. We didn't know what it was. It was like the data stream I showed you at the beginning with the parking meter. Once we figured out, we saw that, we could then measure what's called the bit width, the smallest time of that signal, and determine the baud rate, which was 115.2 kilobits per second. Hook that up to the USB serial adapter, which is like, you can follow the wires over to this thing, and then actually see the data, which I'll show you in the next slide. And then just through trial and error, we knew one of the lines was power, one of the lines was ground. We had the transmit, so we assumed the other one was receive, where we could then start typing commands to it. So it's kind of a typical process. And then here's the power up screen that comes up. It's a first bootloader that does something, maybe unpacks U-boot, and then gets through U-boot and like drops down into a root shell if you can abort the boot process. So now we had root on the device already and didn't even have to do anything, right? So like, hardware hacking sometimes is really easy. So yeah, another really useful tool to have. Then we get into debug tools. So sometimes we'll see these UART interfaces being used to give you debug messages or boot up messages and stuff. But really, what debug tools are used for is taking advantage of programming interfaces on a circuit board that are used usually during the manufacturing process to program the firmware, program the code into the microcontroller. You'll see a lot of these do require physical access, and engineers a lot of times aren't trained in security, and they say, well, I want to make my job as easy as possible. I want to make the manufacturer's job as easy as possible by giving him these interfaces and make it easy for him to be able to connect to, because that's going to save money during manufacturing. If an engineer left these sorts of debug interfaces off of the circuit board, it would be a lot harder for the manufacturing process to get those things working. So it makes it easier for us, which is cool. If we can find a debug interface on a board, either it will be a vendor-specific type of interface, which I'll give you a demo of, or an industry standard interface called JTAG, which I'll also give you a demo of. You can do all sorts of stuff. So you can debug the system just like you would on a software environment. You can single step through code. You can view memory. You can change memory. You can set breakpoints. So if you're trying to identify like where a hash compare is happening or where some password routine is happening, you can figure that out. Or maybe where it's launching some process or loading the kernel, and you want to throw in something that's going to give you a shell on power up. You can do all of that stuff. It's really a powerful interface, and vendors know that. So it's sort of like, how can they protect against that? Sometimes they try to hide the interfaces, but they can't hide it too well because the manufacturers still need it. So there are some secure devices that do a better job than others, but it is like usually just wide open. Once you can find the interface, then you can use some off-the-shelf tools that are recommended by that vendor to start hacking the device. So what do I have? Oh yeah, an example. Okay, so this is an example of using a vendor-specific type of interface. Lots of different chip manufacturers. There's tons of them, right? There's Intel, there's Microchip, there's Atmel, there's AMD. A lot of them will have their own documented, but specific to that type of chip, debug interface, or that type of family of chip. So this one was a project that I had helped Chris and Charlie on for some of their early car hacking work, where they were looking at electronic control units, ECUs, in cars, and wanted to extract firmware from these devices to figure out how the CAN traffic was being sent over the car, so they could figure out, what data meant what. So ultimately, they could do what they did this year at Black Hat of remotely control a car, right? So it's like this was some of the early stages of work. So they sent some hardware to me that both devices happened to be Freescale microcontrollers. And it just happened that Freescale was one brand, one company that I've worked really closely with for a long time. And I have all sorts of the tools already. They have free development tools that I already had loaded on my system. And I already knew about the debug interface that was available for Freescale parts. It was called a background debug mode, BDM. So I basically took advantage of their the Freescale standard programming interface, used the standard off-the-shelf tools, connected up through their IDE, and started manipulating the system. There is an option for these particular devices to have code protection, so to prevent somebody from connecting up with the debug interface once the part is programmed. But for some reason, the vendor did not enable it. Just like, for some reason, a lot of websites, have security disabled by default or whatever it is. And it's like either the vendor didn't think about the fact that somebody would want to get physical access to one of these devices that's like buried deep in the car, or whatever it is. I don't know. But it was totally wide open. So the top one, 2 different boards. One is like a larger board. I don't even know what these are. They never told me. They just sent me the boards and said, give me code. So this is the main chip here. Right next to it was a 6-pin footprint, a 6-pin unpopulated header. And I knew through my Freescale experience that the background debug mode was a 6-pin connector. So I said, all right, I soldered on my own header to that, plugged in my standard development tool, loaded up the debugger functionality of CodeWarrior, and attached myself to that chip, and could then start viewing memory in real time. Oh. Yeah. Yeah, it has nothing to do with the fact that I have my logo stuck onto the thing to give it superpower. I don't know why I did that. It wasn't even intentional marketing or anything. I think it was so no one would steal it from wherever I brought it. Sorry, was there another question? Yes. Oh, that's right. So what we did is once I could connect, I could halt the system and then start accessing memory. And the first one was easy to just connect up and say save memory or view memory, and it would show me the screen here. I could save it to a file. Here I was saving 800 hex to FFFF to an S19 file, a Motorola S record file. That was the entire binary image. So yeah, he was saying you could actually search these numbers and see what sort of ECU it was. This actually, I believe, was the serial number tied to a label on there. So they were programming each device individually with a serial number, which was sort of cool. Another question? That's a foreign part number? Ford. Oh, Ford. Oh, someone knows. That's a Ford. All right, I'm in Detroit, almost.
all those groups mean different things.
Oh, wait.
I never did.
Hold on. I'm going to throw this at you.
But each group might mean it's like a different type of part. Like maybe if it's a body part, it might be AL something F instead of that. But that's what that is, and there is a part number.
So part number as part of the serial number. And you're right. This is from a Ford Explorer, I think it was.
Yeah.
Oh, another question. You want to throw it at him?
I just got a question. How do you get data flowing to your device when it's not connected to the car?
So, right, okay, good question. How do I get data flowing to a device? In this case, there was probably, like some of these connectors were probably going to other parts of the car, other ECUs, sending CAN traffic or whatever, but I didn't care about that. I was connecting directly to the chip itself. So even if it was, it was maybe trying to transmit other stuff, but I'm just going directly to the chip no matter what's around it. Like I could have even taken that chip off of the board and then connected up the pins for the debugger to connect to it. So like debug interfaces, we're basically looking directly at the chip regardless of what's happening outside. And that's what makes it so powerful.
So it's providing, your debugger is providing power for the chip, or is that what the red and black is?
Yeah, so the debugger isn't providing power in this case. Some debuggers, some hardware interfaces can, but usually you would power a device externally. So here I have the power and ground, which I had to just reverse engineer that, just looking at the board and seeing where things connected on the board. And I knew that this chip, I had the data sheet for that chip, so I knew where ground was, I knew where power input was, so I could sort of do some reverse engineering to figure that out. But usually you power the target board separately from your debugger, because the debuggers don't generally have the power capability to provide power to a target, especially because it doesn't know what it is. So yeah, I'm just powering it separately. This board is up doing something, and I'm just connecting directly to it. This one down here is a little bit trickier. Same type of Freescale part, slightly smaller memory size. But on the board, there was no obvious connector. So I said, all right, well, I know the data, I know the part number, I know the data sheet. I'm going to look up the data sheet and see which pins the data sheet tells me are the debug mode pins. Because the data sheet basically gives you all the information that you need about the part. Once I knew the pins, I could take my multimeter, which is a cool test measurement device, and do what's called a continuity test, which basically checks for short circuits. So I took one probe, held it to each pin that I knew was a debug interface, and then moved my other probe around all over the board to see if there was any of the test points that actually were the interface. And it turns out that they all were, just in different spots, right? It's almost like as long as the manufacturer knew where they were, they could create a test fixture to go on top and program it. But from a hacker point of view, it's like, oh, how are we going to find out what that is? And that's the process that we do. So I glued my own connector onto the edge, soldered the little blue wires on, and then connected up. This one was slightly harder because there was some sort of watchdog timer going on, or going off, I should say, where we would power up the board, and like a second or two later, the system would reset. So I'm guessing maybe it was, I thought it was first an on-chip watchdog timer that was looking for the code to reset itself at the right time. So I went in, I had debug access, so I could go and try to change that register to disable the onboard watchdog timer. That didn't work, it was still resetting. So I'm assuming it was maybe looking for data on the CAN bus, and if it didn't see it, it would reset. So I had to sort of work with that and say, all right, I have 1 second or 2 seconds to grab data before it resets. So I ended up coming up with a way of like just dumping smaller sections of code, smaller blocks of code, and like, putting that command into my clipboard and like connecting to the device, pasting it in, dumping it to a file, the system would reset, and I would do like the next chunk. So instead of trying to defeat the watchdog, it's like just work around it to get the code. And then we would concatenate that all back together. And I remember sending that to Charlie. We were on Skype, and I sent it to him. He was like, oh my God, I can disassemble the code. Like, this is awesome. So that was pretty fun. Was it an external watchdog? We don't know. There could have been an external watchdog chip, yeah, maybe somewhere else on the board, like getting, looking to get kicked by something to reset. We don't know. I didn't go into any real, I didn't spend any time really looking once I realized that I could just extract the data. Yeah, that's right. So yeah, the comment was like, if we had a feeling it was an external resetting the microcontroller, we'd find the reset pin on this board, trace it backwards, see where it goes, and it probably connects to an external watchdog timer that's used, to control power up, and then also to reset it if it's not getting kicked at some point. Oh, so many comments. Where's the ball? Who has the ball? Or the cube?
So speaking of watchdogs, have you ever had hardware you're debugging that's actually had some suicide circuit built in, so it detects when you're probing it and it fries itself?
I've heard rumors of devices that have those. So if it's like, hey, if you're trying to communicate, there's actually a tool I'll show you that kind of probes and messes around with lots of different pins, and a system could say, hey, wait a second, I'm seeing a signal on a pin that I shouldn't be seeing. Like maybe I'll do something in response. I haven't actually encountered anything, but I've sort of heard of a possibility of that. But if you're probing a board, you're sort of passively probing with like a high impedance probe, and you're not, as long as you're not sending data to the chip, if you're passively probing and listening, it won't necessarily be able to detect that. But if you're trying to send signals on certain pins that maybe aren't intended to be input pins or something, almost like a honeypot, where it's like, oh, here's an obvious connector, maybe a hacker will send data to it and it will reset. Just rumors, but I'm sure it's definitely possible to do. And then you would like erase memory or do something else in response.
I wanted to mention something about the external reset circuit, that if you have the pinout for the chip in the datasheet, you could just go on the board and slice that trace. Grab a knife, cut that, and prevent the external reset. Then you have to provide your own reset circuit to bring the chip up properly, but that might thwart whatever they're putting in there to keep you out.
Yeah, that's a great point too, especially you just lift it, maybe you have to pull it high or low, and then you just leave it. Yeah, that's a good idea. So lots of different ways, and now we have our code. So vendor-specific interfaces, usually if you're encountering a certain type of microcontroller or system, you would just go to the website and see what they recommend as their recommended type of development tool for that type of platform. Because the vendors want to make it easy for engineers to design and develop with their tools or with their products. They would say, here, use the P&E Microsystems background debug mode device. Like we have a partner with them. You should buy their tool. For vendor-specific stuff. For JTAG devices, which are an industry standard low-level definition of a debug interface, which I don't really go into full detail of what JTAG is here, but we'll just say that it's more powerful than a vendor-specific interface, and we can do lots of really nefarious stuff with it. But first, we have to figure out what the pinout is. So I just mentioned this tool, JTagulator, which is a tool that I designed a few years ago, that basically is like a general-purpose tool with 24 inputs, but I've created a system where you can effectively connect it up to unknown test points on a circuit board or an unknown connector on a circuit board. It's powered through USB. You get a little command prompt through a terminal program, and you can start manipulating and enumerating through all the different possible pin permutations to figure out if there's a JTAG interface or even if there's a UART asynchronous serial interface. So it sort of saves you a lot of the trouble of manually trying to figure that stuff out, which you certainly could do. But this is just to give you the pinout. So it's a tool to help you get a pinout of a JTAG interface. Here's a picture of just one example using an access point. I just randomly hooked up these wires. It doesn't matter what. But down here, I knew that these were very obvious connectors. And then I run the tool and have it do some tricks to determine what the interface is. Now I know the pin numbers. I can enter those in and get a device ID, which is a unique identifier for the chip. I could even then go and Google search this device ID, and that would give me other information about the chip and sort of go from there. But really, the JTagulator gives you the pinout, and then once you have the pinout, then you use other tools that exist that you can then start really messing with the system, even more so than vendor-specific interfaces a lot of times. JTAG basically is it defines this low-level functionality of, it's kind of a state machine, a very simple state machine, sort of a simple CPU where you shift data in, you shift data out. They don't define what can be done above that. But generally, vendors will implement some sort of run control functionality so you can do debugging, give you access to memory. There are some basic functions built in. One's called boundary scan, where you can individually control each pin on the device through a single JTAG interface and also read the pins as the system is working. You won't affect the system a lot of times. Sometimes you will. If you halt the system and then try to do stuff, it might throw things off. But you can do things in circuit as the system is running. So if you think about you have a complex system, say you have a ball grid array device where it's a small device where all of the connections are little solder balls, a matrix of solder balls underneath the part that's then surface mounted to the board. You can't just connect up probes to the edge of the board. You can't even access the pins. If you find the JTAG interface, now you can communicate with that chip. But say there's a memory device that's connected to that chip. Now through that one chip, you can communicate by twiddling all the pins through JTAG of external devices. So it becomes really useful when you're working with highly integrated devices like we see a lot of times with mobile phones and game consoles and consumer devices that are just very small. So once you have the pinout, there's lots of different tools, a lot of open source ones, a lot of commercial ones, because JTAG is this type of environment that legitimate engineers need, but a huge community of people creating some open source tools as well that are very, very useful. Buzz Blaster is a good one. You can even just go to Adafruit and get like the FT232H, which is basically a USB to GPIO, general purpose I/O pin type of interface that provides some synchronous serial functionality as well. So you can have a virtual COM port this way, connect up to your computer, have some tools, software tools running on your computer, and now through this chip communicating through JTAG to boards. And lots of other tools as well. Some are more specific to like Riftbox is really focused on extracting memory from mobile phones. So that's used a lot for mobile phone hackers. Some of them are just general purpose development tools. But the hardware is the one part, but you really need the software to work with the hardware. So it's like this multi-step process, right? You find the pinout, you connect up the hardware, and now you use software tools to really start working with the system. OpenOCD and UART JTAG are the two main ones. Both give you kind of low-level JTAG access if you wanted to start getting the device ID, reading memory, dumping raw memory, and stuff like that. But OpenOCD also gives you a connection to GDB. So if you want to start debugging a system, now you have GDB where you can set breakpoints and do other stuff. This depends on the architecture and what's supported by the chip itself, but a lot of them need some sort of run control so the engineers can actually use it for development or use it for programming. One presentation I would like to reference, instead of giving you a single example, Joe Fitzpatrick and Matt King just gave a presentation at B-Sides. I think they also gave it at 44Con, where they're basically showing like, all right, once you have JTAG access, what things can you actually do to get root, to gain full control of the system? And that's the important step. So I talked about accessing memory. Those are easy ones. You can also patch boot arguments of a system, so you can halt the system at a certain point, modify what's going on at boot to cause a device, change memory to have you load a shell, patch the kernel, change access control stuff. Just amazing things. So check out all their tools are up there. Their presentation is up there. There's no live video yet, but eventually I think they'll put a video up once it's recorded at a presentation. But yeah, you can do a lot. And this is really the key if you're working with a complex embedded system, that you're not really going to necessarily use your soldering iron and probe around too much because it's just too complex. You find JTAG, you start hacking some Linux system, you're patching things, and then you get root and you win. So two other tools related to that, related to finding debug interfaces, manipulating serial devices, are the Bus Pirate and the GoodFet, which I'll show you next. These are devices that were created by the hacker community, intended to be kind of serial interface, serial manipulation types of devices. So if you find an interface that has whatever serial protocol, you can connect to it and start communicating with the device. You can also do some kind of basic logic analyzer functionality, some JTAG, but usually it's pretty slow. But it's a good tool to have in your toolbox for just kind of messing around and saying, oh, I wonder, here's an I2C interface between two chips that I've now sniffed, either with my logic analyzer or with this tool. What's going to happen if I send different data over those lines, right? And spoof connections, and this tool will let you do that. Same with the GoodFet, which was created by Travis Goodspeed and sort of begun as a more capable version of the Bus Pirate. And it's been expanded by the community now to support all sorts of different serial interfaces. It even serves as a device programmer to certain types of chips, so PICs and AVRs, but also lots of RF-related chips as well. So it's an amazing tool. I believe Travis will still give these to you for free, or he'll mail them to you, just bare boards. And the exercise is that you have to solder them yourself in order to make it work. So if you find him at a conference, you maybe trade him a beer or something like that. I think he likes beer. Here's an example. This is an IME device. It's been used for all sorts of different hacks. It's like a messaging device targeted towards like young teenage girls. And it didn't do very well in the market, so they were basically available for like $15 or $20 on eBay. And it had a ChipCon, I think 1101, or some sort of ChipCon wireless module in it that had an 8051 microcontroller, totally hackable. There was a debug interface on the back of the board. So Travis had written some tools that you could use the GoodFet and like reprogram new firmware in. Now there's a whole API for hacking the IME, and like you can control the display, you can read the keypad, and write your own programs for this device. Sammy Comcar just gave a presentation at DEF CON about I think he calls it Open Sesame, which is his tool that replays a bunch of the fixed code garage door opener systems, all using the IME. And once he gave that presentation, the price on eBay went from like $20 to like $300 or something. So thanks, Sammy. Now we can't get them. But yeah, so a really, really cool platform. And Travis, just made it that much easier by writing the tools to give you access to reprogram that. So lots of stuff there. Very powerful tool. Okay, so I just threw in a bunch of like extra stuff talking about imaging. All the prior stuff was really require physical access, or maybe we're listening on wireless. But a lot of hardware hacking starts with initial analysis of a system, or maybe if we need to reverse engineer what's inside, or maybe the housing is filled with epoxy that we can't get to the circuit board. Or there's some sort of anti-tamper mechanism where if we open up the housing, it's going to detect that and erase memory. So we go through like a kind of imaging step first of non-destructively looking at the device, seeing if we can get any clues by locating switches or seeing through and finding the location of chips underneath the epoxy or whatever it is. Maybe we want to reverse engineer the circuit board, which is going to give us the whole story of how the system electrically works. We would do a lot of this stuff. So more advanced techniques, but something that is possible and that is done a lot of times. And these are things, obviously, like most people don't have an X-ray machine in their house, though a few people do. I think Ben Krasnow just created his own X-ray machine. A few other guys have gotten like dental X-ray, little smaller X-ray machines to mess around with. But usually, like you would go to a contract manufacturer, a company that manufactures circuit boards. In Michigan, I'm sure there's tons of them all around the automotive. But any major city is going to have somebody that assembles circuit boards. Usually they'll have an X-ray that's used for testing ball grid array devices to look through the board and make sure there's no solder joints on chips that you can't normally visually look at. So you go to them and say, hey, I would like to rent some time on your X-ray, and they would say, sure, $100 an hour, or $250 an hour, and they'll do it. So it's totally cool. They make money, so why not offer that service? And a lot of times they will. So X-ray, as you probably know, gives you this composite image of everything. So it's hard to tell sort of X or Z axis of what's going on, but it's still a great way to give you this visual identification. So usually, again, it's used for verifying soldering quality and for PC board assembly, but we can use it for general inspection and finding hidden clues and stuff. A good example is like if we're looking at a BGA, a ball grid array device, we have a data sheet for it. We want to see where the JTAG pins go, or where the debug interface pins go, or where maybe there's an unconnected USB interface that we might want to try to tap onto and connect up to. We can use X-ray. Instead of taking the part off the board and visually tracing where things go, we use X-ray and say, all right, these are the pins I want. Like, let's follow those traces out, see where they go. That makes it easier for us to then tap onto. We won't know which layer of a circuit board it's on, because circuit boards a lot of times are multi-layer, but we can eventually get an idea of like, oh, that goes to a giant hole, test point. Let's connect to that. So X-ray is really good for that. You can also maybe take a guess at layer count. Here's one I was inspecting an active mesh, an active shield circuit board that was on top of a pin pad. So acting as a tamper mechanism. So if I open up the board and took this cover off that was protecting circuitry, the system would erase itself. So I did some reverse engineering and X-rayed it first and realized it was this crazy 4-layer board of like mesh, like a maze of wires and stuff. And that's the first step in kind of the analysis process. One level, I guess, better than 2D X-ray is 3D X-ray or CAT scan. Some of you guys have probably had CAT scans before, and yeah. And they're usually not that fun. They're fun the first time, I think, but probably not after that. But basically, a CAT scan or 3D X-ray takes lots of two-dimensional X-rays at a certain angle, at a defined angle across the object. And then with a bunch of post-processing math magic, you'll be able to see slices in different axes, in the X, Y, and Z axes. So that's how you can see, slices through a brain or through a body part or whatever. Traditionally, these types of systems are used in companies that specialize in failure analysis, looking at boards that have broken or systems that have broken to try to figure out what's wrong. Usually it ends up being like a solder related problem, a cracked solder ball, or a component is cracked that you can't see, and you can see that in a CAT scan. But we can use it to actually reverse engineer a board and get individual layer images from a board without having to physically destroy it. I have a whole separate presentation about like deconstructing techniques of circuit boards to get access to the different layers, because if you can recreate that image, you can then figure out exactly what components are connected to what and put together a full image of like how a system works. But a lot of times you don't want to do that, right? You just want to get a better sense without messing with the components. So this way you can actually do a CAT scan of a circuit board, and it usually works. And this is some work I did with a company that they'd never done any circuit board reverse engineering, but they specialized in failure analysis. And I call up the CEO of the company, referred by the contract manufacturer I use. And it turns out I woke him up while he was at a conference in Germany. It was like 3 a.m, Germany time, when I call him. And so I heard the normal ringtone, and then I heard the ringtone switch to the like international ringtone, and I'm like, oh no. But by that point, it was too late. Like he had already answered the phone. So we joke about that all the time. But it was like, I was like, hi, my name is Joe, and I'm like reverse engineering circuit boards. Do you guys want to help? And he was like, yeah, like that sounds really cool. So we ended up meeting up a little bit later, and now it's a service that he provides of actually helping people reverse engineer circuit boards based on this work. So it's like, there's always places to learn, right? There's always some new technique to learn. So this is just an example of a 4-layer circuit board that I designed, and then the resulting, so I had these images already, and then the resulting CAT scan images from the different layers. And they're pretty good. And of course, like you only get like a small field of view when you do that, so you would have to go through a whole bunch of areas of the board and patch them all together. But like, I don't know, that's not a big deal. And here's a video of that. So here I put together a video of looking through from the top of the board down and looking through the different layer images as we go. So here's like, we're coming in from the top of the board, looking slice by slice, and you'll see layer 1 come up right away, coming into focus. So there's layer 1, there's layer 2, and now we go through most of the circuit board, the substrate, the middle part of the circuit board, which is fiberglass, and then we'll see layer 3 come up. It was very quick, and then layer 4. So you're really just cutting through the board and looking. So pretty powerful stuff. And then getting into chip hacking, we talked about this at the beginning. Scanning electron microscope and focused ion beam machine are the two that are really used. Like if you need to get real chip level high magnification, this is what you would use. So of course you need to, like with a chip, you need to remove the plastic packaging to get access to the silicon die underneath. And there's all sorts of other techniques to do that. It's usually chemical and mechanical stuff to get through. And if you do that properly, the chip will still function. So then the chip is opened, and you can start looking and identifying areas of the board. That's a whole other area. But if you look at Chris Tarnowski's presentations from Black Hat, Olivier Thomas is another one who has given some presentations about chip hacking. There's a lot you can do. So this scanning electron microscope here is like part of an old, I believe this was like some sort of masked ROM, like hard-coded ROM from a smart card, where you can like visually recreate the 1s and 0s that were stored in there. So say that was like a bootloader that was fixed in memory that you wanted to figure out how the bootloader is working. You recreate those 1s and 0s back into code, disassemble that, and see what's going on. Or maybe it's a crypto key. Maybe it's like a private key shared across every device that's hard-coded in there. Like people do stuff like that. And at a chip level, you can't really hide. You can also do even crazier stuff like voltage contrast microscopy, which lets you visually see gate charges, so highs and lows, 1s and 0s on a bus. I don't know how often that technique is used for hacking, but it's also pretty cool. Way over my head. And here's Chris Tarnowski's old lab in his basement. Totally normal, right? And this was something that he built up over years. He ended up selling this setup to IOActive, so they actually have a chip hacking lab as well, and I think he's building up his own. So there are more and more people starting to do chip hacking stuff. But a focused ion beam machine lets you do imaging, but it also lets you cut traces like we would cut with a knife or something, and then deposit, reconnect traces like we would do with solder. So if there was, say, a security bit or some sort of security fuse that was physically blown on the chip to prevent you from reading contents of data back out, you could go in, repair that connection, and then read the contents back out. Or maybe, re-enable a debug port that was physically disabled on the die or something like that. There's all sorts of stuff. Chris Arnowski gave a presentation of hacking a trusted platform module, a TPM, that had like various layers of active mesh that he was able to basically using cutting and depositing, opening the mesh. So keeping it that the connections were still there, but moving them out of the way so he could then go down different layers and start listening in on address and data bus lines, doing glitching on signals and things. Basically what we would do at a board level, but now at like a super low level chip level. So insane. I'm guessing University of Michigan has some tools like this. Okay, so that's I don't know how long that was, but that's a handful of the tools to get you started. I guess sort of the question is well, what do you do now? If you are getting, if you're curious about hardware hacking, if you want to build up a lab, get some of these tools, start hacking. A lot of presentations out there, learning from history. You'll see a lot of types of attacks that are just poor implementations over and over again, done by different engineers across different platforms, similar classes of attacks as far as debug interfaces, poor memory, usage of memory. Even companies that have implemented a good secure boot process of having some authenticated code or decrypting something and then putting it into memory, those can still be bypassed because, say in the case of JTAG, if we halt the system after the kernel has been decompressed and unencrypted and checked, now we have access to the clear text kernel that we can mess with. So it's even if companies have tried to do it right, maybe they haven't. Meet with other people, and possibly you want to use these to check your security, maybe break other people's security, whatever it is. The tools are out there now. It's just up to you guys to do something with them. Any questions? Yeah. Well, where's the box thing?
So I'm curious. With some of this equipment, I'm paranoid. I use USB isolation. Do you have any horror stories of when you've gotten your really good equipment fried on some of the circuits?
Yeah, so not through USB, but there was one device I was reverse engineering, which was a heat sealing, like a heat sealer for a consumer project. And I was reverse engineering some of it, and it was like a wall plug device. And I don't remember how I had things hooked up, but I was using my oscilloscope to probe on things, and I put my probe on something, and I wasn't isolated, and luckily I didn't destroy my oscilloscope, but there was a huge spark, and I blew a trace on the board that was serving as a fuse. So yeah, having good isolation is probably good, and understanding what you're connecting to. I haven't really worked with wall, mains supply circuits, and I probably never will again after that. But it's there's some ground that it should have been connected or something. But yeah, usually if you're working with a wall mains supply, you'd maybe want to isolate that system from ground, or maybe have USB isolation. But it sort of depends on the system. But yeah, you always have a risk of, as you're probing things or poking around that, you could possibly damage something. And usually if you're hacking on a system, I would always recommend try to get 10 units, have one gold standard, and use the other ones for research.
Yeah, so I didn't actually bring a notepad today. Is this lecture, or the slides, are they available online, or?
Yeah, so the slides are on my website, which is grandideastudio.com. Search for tools of the hardware hacking trade or whatever,
Okay.
and they'll be there. And then the YouTube video is up already, thanks to the future of the internet and to Duo. It's already there.
Right on.
So you can quote me forever or misquote me or do whatever you want. Any other questions?
I wanted to throw one more. Back to the isolation topic. EEV blog. Dave Jones has a really great little. I think it's about 20 minutes long, called either "How to Blow Up Your Oscilloscope" or "How Not to Blow Up Your Oscilloscope." I forget what it's called.
I should have watched that first.
Yeah, but it's about exactly that, and it's really good.
Yeah, so. Cool. Oh, more. John O has one. Throw it hard.
So if you're starting off, are there communities you can join of shared hardware tools to find you don't want to make a big investment, you want to go in with a bunch of people, or rent out tools?
Sure. So yeah, thankfully with hacker spaces these days, maker spaces, or whatever you want to call them, there's places you can go what was it, I3 Detroit? Outside of Detroit.
I3 Detroit.
Basically, if you go to, I think it's hackerspaces.org, there's like a wiki of all different hackerspaces, and most of them are public as opposed to like when I was involved in one a long, long time ago, like it was more of a private thing. Nowadays, these spaces exist for you to go and learn, and if you don't know about how to use an oscilloscope, you can ask somebody, and generally, they'll be helpful and say, hey, here's how you use it. Let me help you hack the system. So there's lots of groups. Of course, at DEF CON, there's Hardware Hacking Village. At other conferences, there's villages. Lots of forums online. EEV blog forum is a great one. Adafruit has forums. I think SparkFun Electronics. So lots of different ways to get involved, and lots of people willing to help. And you can always email me too. Another?
Yeah. Do you think there's any value to like part etching or putting epoxy on boards, or is that sort of just a weak defense? Not as the only defense, but
it depends. Like most security, you want to have layers, right? You don't want to put all your eggs in one basket, and you don't want to have everything, just protected by one thing. There are sometimes I've encountered systems that use epoxy, but they're used totally wrong. So it's easy to either, you don't even need to mess with the epoxy, or you just scrape it off, it's easy. There's other systems I've encountered that are like half-inch thick blocks of epoxy. And that's gonna change your attack scenario. But that costs money, right? So if you can convince management to pay for that extra service, that's a good thing. A lot of times you won't see that in systems because it's an extra cost of like, well, why should we secure ourselves? Let's wait until we get hacked and then do something about it. So that's sort of the common approach. If you can implement it, that's great. And I feel like it's better than nothing. Though yes, sometimes it gives you this false sense of security of like, oh, we have epoxy, no one's gonna hack it. But if you do have epoxy, it usually makes it slightly harder, right? So it's like locking your car door as opposed to leaving it unlocked. Someone could still break in, but it's just like slightly harder. Now they have to, break the window instead of opening the door.
and maybe they'll break into someone else's car.
And maybe they'll break into someone else's car, right? It's like if it's an opportunistic sort of thing, it's like you make it hard enough, maybe they'll go somewhere else, or maybe it becomes a challenge where they want to look at it. So you can't really tell. But I would say in general, if you have the power to implement those sorts of features, by all means do it, and just to make yourself that much better. And there are also things like FIPS 140 has a standard for security, for hardware security, and I wouldn't necessarily say that that's a good stamp of approval, but they have some guidelines that are worth checking out if you are on the design side, just to make you better, right? It's like, there's so many, I just read on the way here, a survey of companies that were like worried about security, and only I think 50% of people that responded were like, yeah, maybe security is like something we'll worry about in the future. And like, it should be 100%, given all the stuff that's gone on, right? So it's like, if you can be in the upper 50%, like that's pretty good. Oh.
So I have 2 teenage boys at home who take all my stuff apart. So how can I get them involved? What's a good place to get them started with breaking maybe somebody else's stuff?
Well, first you have to get somebody else's stuff, right? Yeah, I would say, first of all, it's great that they're destroying everything. I'm sorry it's yours. Yeah, you definitely want to foster that, right? So it's like, find a hackerspace. What I do with my kids is like, if I see something on the corner that somebody has thrown out, like I'll bring it home and let them open it up. So it's, it's a little, we don't know what we're going to encounter. Or if I end up breaking something by accident, like we'll open it up together to learn how it works. Maybe hackerspaces, maybe there's like an electronics meetup. In Portland, there's Dorkbot is a group, which is also around the country and other places, more of like an electronics. I think the tagline is like people doing weird things with technology or something like that. But just finding other like-minded individuals and have them, if they encounter something and really want to start hacking it, get some of these tools and say, all right, maybe buy them an old access point on eBay for $20 or at a surplus store or something and say, here's the access point, here are some tools, go online, try to figure out how to hack it, how to get root access, how to get memory. Basically sort of guide them along the way and see what happens.
And not a lot of experience hardware hacking, but it seems like there's a lot of entry vectors. There's a lot of like exploit primitives that you might have as you're going about looking at a circuit board or injecting or glitching or rememory, whatever else. A while back,